There's a simple game played with just two numbers, 1 and 0, which after only a few rounds becomes mind-bogglingly complex.
One of the things that's cool about this problem is its depth. It's a fun game to play.
It's a puzzle that asks this about a computer program.
What's the longest, most complicated thing it can do and then stop?
It's called the Busy Beaver problem.
It's a busy beaver in the sense that it's doing so many operations that at some point it stops.
This simple game is connected to some of the thorniest questions in math and computer science.
Just as hard as the hardest open problems in mathematics.
But recently, a motley group of amateurs came together online to tackle the toughest version of the problem to date.
It's like candy for me or something, people nerding out about this thing.
They ended up solving this long-standing open question faster than anyone thought possible.
Kind of a brave and slightly crazy thing to do.
So how is the Busy Beaver game played? And what was the secret to the team's success? The Busy Beaver game was formulated by the Hungarian mathematician Tibor Rado in 1962. Rado was exploring the behavior of theoretical computational devices called Turing machines.
One of the simplest formal models of a universal computer.
Turing machines were conceived in the 1930s by the mathematician Alan Turing. All Turing machines contain three components: an infinite tape that stores data in cells as ones or zeros, a head that reads the tape, writes a new number onto it, and moves the tape left or right, and a set of instructions or program that tell the machine exactly what to do at each step. Turing machines are capable of computing anything that is computable by algorithms.
By doing this very simple but sort of esoteric set of instructions, you can do just as much as you can do with any other programming language.
A Turing machine's program can have any number of rules, as summarized in a table. This table contains one row for each rule and two columns, one for when the head reads a 0 and the other for when the head encounters a 1. Each rule tells the machine what to write, which way to move the tape, and what rule to follow next. All computer programs either perform their function and eventually stop, known as halting, or they get stuck in infinite loops and run forever.
Useful programs are programs that stop.
Here's an example of a two-rule Turing machine that halts. At the onset, all cells on the tape are set to 0, and it's set to follow Rule A. The head reads the tape and encounters a 0. The machine then looks up the rule in the 0 column. The instructions say to write the number 1, move one cell to the right. The next rule to follow is Rule B. After writing the number 1, the machine then moves the tape a cell to the right and encounters another 0. The 0 column in Rule B instructs the machine to write a number 1, move one cell to the left. The next rule to follow is Rule A. The Turing machine moves the tape a cell to the left, and this time encounters the 1. The Rule A instructions in the 1 column tell it to halt. Here is a two-rule Turing machine with different instructions, which will cause it to never stop. It quickly gets stuck in an endless loop. Computer scientists want to know, given the rules of a Turing machine, is there a guaranteed way to tell whether that machine will halt or run forever? This question is known as the halting problem, and it can be extremely hard to solve. The halting problem is at the heart of the Busy Beaver game.
In some ways what we're doing, we're trying to solve a little subsection of the halting problem. Take a bite, out of it.
The Busy Beaver game works like this. First, pick a specific number of rules for your Turing machines, denoted N. This number determines how many Turing machines will exist in the group, where each machine has one distinct set of rules. For example, with only one rule, there are 25 Turing machines, each with a unique program. However, many of them will do the exact same thing. With 2 rules, there are over 6,000 distinct machines. And for n equals 3, or machines with 3 rules, there are millions. Now feed a tape of zeros into each machine in the group and see what happens next. Some will halt quickly. Others will run much longer, while still others will keep going and going forever. For each value of n, there must be one hard-working machine that runs the longest and then stops. This is the Busy Beaver. The number of steps that the Busy Beaver with n rules takes before halting is denoted BBN. The goal of the Busy Beaver game is to identify the Busy Beaver for a given group and determine how long it runs before halting. For the group of one-rule machines, BB1 is easy to determine because there are essentially only two outcomes. If the rule tells the Turing machine to halt when it encounters a 0, it will stop on the very first step. Turing machines with any other set of rules will keep moving down the tape of zeros forever. This means that the solution to BB1 is one step. The Busy Beaver value for a two-rule Turing machine is 6 steps. For BB3, the longest running machine that still halts runs for 21 steps. But when you get to BB4, things start to get more interesting.
Now you're getting Turing machines that can start to do pretty complicated things.
With 4 rules, there are billions of Turing machines to sort through and evaluate. And for some of these machines, the halting problem is fiendishly difficult. To many, BB4 seemed unsolvable. But in 1974, computer scientist Alan Brady finally succeeded. He determined that the Busy Beaver for a 4-rule Turing machine runs for 107 steps. For decades, BB4 looked like the end of the road. But then a French graduate student named Tristan Sterrin entered the picture. After reading an article by computer scientist Scott Aronson, Sterrin got hooked on BB5.
It failed hard enough, but not too hard. It's what you want in an open problem.
So in 2022, Sterrin created a website dedicated to solving BB5 and named the endeavor the Busy Beaver Challenge.
We have to create a tool so that people can start working on the problem so it's less overwhelming. It's not just one person, it's more distributed.
Word soon got out about the challenge, and people from all over the world joined in.
The hope was to build a little scientific community.
But with 5 rules, there are nearly 17 trillion possible Turing machines. Where do you even begin the search? The hunt for BB5 has a long history. In 1983, nearly 100 people gathered in the West German city of Dortmund for a competition to find BB5. But ultimately, they all fell short. However, 2 Busy Beaver hunters, graduate students Heiner Marxen and Jürgen Buntrock, continued the hunt. With a powerful new computer, they identified a possible contender, which halted after a staggering 47,176,870 steps. The pair conjectured that this was, in fact, the 5th Busy Beaver. But they couldn't prove it. Marxen and Buntrock's 5-rule contender gave the Busy Beaver challengers a starting point. Now the team needed to devise methods to prove that no machine exists that runs longer than this contender and still halts.
So the first step was to construct a database of 5-state Turing machines with the properties that they are the only machine you need to consider.
Sterrin wrote a computer program that winnowed the list of trillions of machines down to 88 million. All the rest were either redundant or halted before Marxen and Buntrock's machine.
And phase 2, it was to invite people to write programs that we call deciders.
These deciders analyze machines to determine whether they will eventually halt or run forever.
A sufficiently good new decider might eliminate 90 to 99% of the remaining unsolved machines, so it's a huge impact.
To verify the accuracy of these deciders, the decentralized group of around 20 challengers, some of them anonymous, devised a validation system.
Someone else has to reproduce your results independently, and then you have to write in a formal mathematical way.
Using deciders, the group reduced the list of contenders to around 30 holdouts, which couldn't be cracked with computers, requiring a different approach.
Attack each of these one-off and try to prove, manually that this specific machine never halts.
Over the following months, the team communicated through Discord forums and posted their progress to the BB Challenge website.
We would be getting updates about, we're down to 15, we're down to 6 machines, And eventually, it got down to 1, which was one of the hardest ones to prove.
Finally, they had tentative proofs for all machines. What remained was the arduous work of verifying everything. But then in April of 2024, a mysterious new contributor, known only by a pseudonym, joined in to finish the job.
Somebody with the handle MXDYS showed up on the forum and basically said, like, hey, I have written a Coke proof.
Using a computer-assisted proof verification system called Coke, MXDYS swiftly completed the challenge.
In about 1 month or two, had formalized everything we had done and more to come to a final solution.
It turns out that the contender identified by Markson and Buntrock 30 years earlier, which halted after 47 million steps, was the fifth Busy Beaver after all.
Now we have the computer-verified proof, and we are working on the human-readable proof.
The way that this happened was because of the collaboration in the community, sharing their ideas, bouncing those off of other people. It couldn't happen without it.
Meanwhile, part of the team has moved on to new endeavors.
The most straightforward one is, well, can we find the six-state champion?
However, with the addition of just one rule, the Busy Beaver problem becomes much, much harder. There are nearly 60 quadrillion possible six-rule Turing machines. One specific machine is especially vexing. The question of whether it halts resembles a famously intractable math problem called the Collat's conjecture.
Maybe 6 is something which no group of human beings, no matter how crazy and obsessed and dedicated they are, will ever calculate.
Currently, it seems that it's quite impossible to solve BB6, but people said that for BB5.